What if I told you that the force pulling you down right now is the same force that keeps galaxies from flying apart? What if I told you that understanding this invisible hand took humanity over 2,000 years of genius, failure, and pure stubbornness? And what if I told you that we still don't fully understand it? Welcome to the most mind-bending story never told properly, the history of gravity. Before we dive in, let's destroy the biggest myth in physics right now. Newton did not discover gravity when an apple fell on his head. That's like saying Columbus discovered America by accidentally bumping into it with his face. The truth? Newton's apple story is way more interesting than the fairy tale version, and it all starts with a plague. Picture this. You're an ancient human. Things fall down. Always down. Never up, never sideways, just down. Why? Your best guess? The gods are angry, or maybe the earth is hungry. For thousands of years, this was literally our best explanation. But then came the Greeks, and oh boy, did they have opinions. Aristotle, the guy who was wrong about almost everything but somehow convinced people for 2,000 years. He thought heavy things fell faster than light things. Makes sense, right? A rock should fall faster than a feather. Here's the kicker. Aristotle never actually tested this. He just thought really hard about it and declared it true. This is like deciding the best pizza topping by staring at a wall instead of, eating pizza. But hey, when you're Aristotle, apparently thinking equals science. Fast forward 1,800 years. Enter Galileo Galilei, a man so fed up with Aristotle's nonsense that he literally climbed the Leaning Tower of Pisa just to prove him wrong. Legend says he dropped 2 balls of different weights from the top. And guess what? They hit the ground at the same time. Now, I say legend because historians aren't 100% sure this actually happened. But you know what definitely happened. Galileo rolled balls down inclined planes in his workshop, timing them with his pulse because stopwatches hadn't been invented yet. This guy was so dedicated to proving Aristotle wrong that he turned his own heartbeat into a scientific instrument. That's commitment. But here's where it gets really interesting. Galileo didn't just disprove Aristotle. He discovered something that would blow everyone's minds. All objects fall at the same rate in a vacuum. A feather and a hammer will hit the ground simultaneously if you remove air resistance. Don't believe me? NASA literally proved this on the moon in 1971. Commander David Scott dropped both items during Apollo 15, and sure enough, they landed together. Take that, Aristotle. While Galileo was dropping things and making Aristotle roll in his grave, something even more revolutionary was happening. Mathematics was getting scary good. People like Kepler were discovering that planets moved in ellipses, not perfect circles. Descartes was inventing coordinate systems. The stage was being set for someone to come along and put it all together. But first, let's talk about Johannes Kepler for a hot minute, because this guy deserves way more credit than he gets. Kepler spent years, and I mean years, trying to figure out Mars's orbit. He had thousands of observations from his mentor Tycho Brahe, and he was convinced Mars moved in a perfect circle around the sun. Spoiler alert, it doesn't. After 8 years of calculations that would make modern mathematicians weep, Kepler finally gave up on circles and tried ellipses. Boom. Perfect fit. But here's the crazy part. Kepler had no idea why planets moved in ellipses. He just knew they did. He discovered the laws of planetary motion without understanding the force that caused them. It's like figuring out the rules of a game by watching it, but having no clue why the rules exist in the first place. Now we get to the real Apple story. The year is 1665. London is being decimated by the plague, and Cambridge University has basically shut down. A 23-year-old Isaac Newton, yes, he was just 23, which should make you feel terrible about your life choices, heads home to his family farm in Woolsthorpe. What happens next is arguably the most productive work-from-home period in human history. During these 18 months of isolation, Newton invents calculus, discovers the laws of motion, begins working on optics, and, oh yeah, by the way, starts developing his theory of universal gravitation. The apple didn't fall on his head. What actually happened, according to Newton himself, is that he saw an apple fall from a tree in his garden and had a thought. What if the force pulling that apple down is the same force keeping the moon in orbit around Earth? This was a wild idea, absolutely insane. Nobody had ever suggested that earthly forces and celestial forces were the same thing. The heavens were supposed to be perfect and unchanging, while Earth was messy and chaotic. But Newton thought, what if it's all just one force? So Newton does something brilliant. He decides to test his crazy idea mathematically. If the same force pulling apples down is keeping the moon in orbit, then he should be able to calculate it. Here's his logic. The moon is falling toward Earth constantly, but it's also moving sideways fast enough that it keeps missing. It's like the world's most successful failure. The moon is perpetually falling and perpetually missing Earth. Newton calculates how far the moon should fall toward Earth every second, if his theory is correct. Then he calculates how far it actually curves in its orbit. The numbers almost match. Almost. This is where most people would give up or fudge the numbers. Not Newton. He realizes his calculation of Earth's radius is wrong. He waits for years until better measurements of Earth's size become available. When he recalculates with the correct radius, the numbers match perfectly. The moon is falling toward Earth. It's just moving too fast to hit us. This realization connects earthly gravity with celestial mechanics for the first time in human history. But Newton doesn't publish any of this yet. Why? Because he knows it's going to be controversial. Really controversial. He's essentially saying that the same rules governing a falling apple also govern the planets, the stars, everything in the universe. Plus, there's a technical problem. Newton's theory requires something called action at a distance, the idea that objects can influence each other without touching. This sounds suspiciously like magic to most people. How can the sun pull on Earth across millions of miles of empty space? What's doing the pulling? Newton doesn't know. He admits he doesn't know. But the math works perfectly, and that's gonna have to be enough. Little does he know that he's about to revolutionize not just physics, but the entire way humans understand their place in the universe. And it all started with a guy in quarantine, watching fruit fall from trees. When we left our hero Isaac Newton, he was sitting on the most revolutionary scientific discovery in human history and doing absolutely nothing with it. For nearly 20 years, Newton kept his gravitational theory mostly to himself. Why? Because Newton was, to put it mildly, not great with people. This is a guy who once stuck a needle in his eye socket just to see what would happen to his vision. He stared at the sun until he nearly went blind, again, for science. He was brilliant, obsessive, and had the social skills of a particularly antisocial hermit crab. But then something happened that forced Newton's hand. Edmund Halley showed up. Edmund Halley, yes, the comet guy, was everything Newton wasn't. Charming, social, wealthy, and most importantly, he knew how to get things done. In 1684, Halley visited Newton with a question that would change the world. Halley asked, if gravity follows an inverse square law, what shape would planetary orbits be? Newton immediately replied, ellipses. Halley was stunned. How do you know? Newton, because I have calculated it. This is the 17th century equivalent of someone casually mentioning they've solved world hunger while you're asking for directions to the grocery store. Halley demanded proof. Newton couldn't find his original calculations, because of course he couldn't. This is Newton we're talking about. So he promised to redo them. What he sent Halley a few months later wasn't just a proof. It was a 9-page treatise that would eventually become the Principia Mathematica, arguably the most important scientific book ever written. The Principia, published in 1687, didn't just present Newton's law of universal gravitation. It completely rewrote the rules of how to do science. Before Newton, natural philosophy was mostly about coming up with clever explanations. After Newton, it became about mathematical prediction and experimental verification. Newton's three laws of motion, combined with his law of universal gravitation, could predict the orbits of planets and comets, the timing of eclipses, ocean tides, the precession of equinoxes, why Earth is slightly flattened at the poles. This was unprecedented. For the first time in human history, someone had created a mathematical framework that could predict the behavior of everything from falling apples to distant planets with incredible accuracy. But here's what made the Principia truly revolutionary. Newton didn't just describe what happened, he explained why it happened, using fundamental principles. Every object in the universe attracts every other object, with a force proportional to their masses, and inversely proportional to the square of the distance between them. That's it. One simple equation, governing everything. Of course, not everyone was thrilled with Newton's ideas. The scientific establishment had some serious problems with universal gravitation. First, the action at a distance problem. How could objects influence each other across empty space? It seemed like magic, or worse, it seemed French. This was a serious concern in 17th century England. Second, Newton's theory implied that space was absolute and infinite. This was philosophically troubling. If space goes on forever, where does that leave God? What's beyond the edge of an infinite universe? Third, and perhaps most damaging to people's egos, Newton's theory suggested that humans weren't special. The same laws that governed our mundane earthly existence also governed the majestic heavens. We weren't at the center of a unique, divinely ordered cosmos. We were just another rock orbiting an ordinary star in an infinite universe. The French, led by René Descartes' followers, were particularly resistant. They preferred a theory where planets were carried around by invisible vortices in the ether. This seemed more natural than mysterious forces acting across empty space. But Newton had something his critics didn't: accurate predictions. His theory didn't just explain things after the fact, it predicted things that haven't been observed yet. The first major vindication came in 1705, when Halley used Newton's laws to predict the return of a comet he'd observed in 1682. Halley calculated that this comet had an orbital period of about 76 years, and predicted it would return in 1758. Halley died in 1742, so he never saw his prediction vindicated, but in 1758, right on schedule, the comet returned. It was the first time anyone had successfully predicted the return of a comet, and it made Newton's theory famous across Europe. But the real vindication came with something called the three-body problem. Here's where Newton's theory got really impressive. It's relatively easy to calculate the orbit of one object around another, like Earth around the Sun. But what about three objects all influencing each other simultaneously? This is fiendishly complicated. The gravitational forces are constantly changing as the objects move, which changes their paths, which changes the forces, which changes their paths. It's a mathematical nightmare, but Newton's theory handled it. Astronomers could predict not just where planets would be, but how their orbits would be affected by the gravitational pull of other planets. They could calculate the complex dance of Jupiter's moons, the precession of Mercury's orbit, even the slight wobbles in Earth's rotation. This level of mathematical precision was unprecedented in human history. Newton had essentially created a clockwork universe where everything could be calculated if you just knew the initial conditions and had enough time to do the math. But Newton's success came with a cost. The Principia was so mathematically complex that very few people could actually understand it. Voltaire supposedly said that in all of England, there were no more than 20 people who could follow Newton's mathematics. This created a weird situation, where Newton's ideas became famous and accepted, without most people actually understanding them. It was like everyone agreeing that quantum mechanics is correct, while having no idea what quantum mechanics actually says. Newton himself became increasingly isolated and paranoid. He spent more time on alchemy and biblical chronology than physics. He got into bitter priority disputes with other scientists, most notably Gottfried Leibniz over who invented calculus first. The man who had unified heaven and earth, who had revealed the mathematical structure underlying all motion in the universe, spent his later years as master of the Royal Mint, obsessively hunting counterfeiters and trying to turn lead into gold. But his legacy was secure. Newton had shown that the universe operated according to precise mathematical laws that could be discovered and understood by human reason. He had created modern physics, and in doing so he had fundamentally changed how we see our place in the cosmos. The universe was no longer mysterious and capricious. It was a vast, intricate machine operating according to discoverable rules. And at the heart of this machine was gravity, the universal force that shaped everything from the fall of an apple to the spiral of a galaxy. But as we'll see in the next hour, Newton's clockwork universe was about to face some serious challenges. The 18th century was drunk on Newton, and I mean absolutely, completely intoxicated. Newton's success with gravity had convinced everyone that the universe was basically a giant, predictable machine. Given Newtonian physicists the position and velocity of every particle in the universe, and they claimed they could predict the future with perfect accuracy. This wasn't just scientific optimism, this was a complete worldview. They called it the clockwork universe, and it was intoxicating. Suddenly, everything seemed knowable, predictable, controllable. Pierre-Simon Laplace, the French mathematician, put it best. We may regard the present state of the universe as the effect of its past and the cause of its future. An intellect which at a certain moment would know all forces that set nature in motion, would be able to comprehend the motions of the largest bodies of the universe and those of the tiniest atom. For such an intellect, nothing would be uncertain, and the future, as the past, would be present before its eyes. This hypothetical, all-knowing intellect became known as Laplace's demon, and it represented the ultimate dream of Newtonian physics: perfect knowledge, perfect prediction, perfect control. Armed with Newton's laws, 18th and 19th century astronomers set out to map the heavens with unprecedented precision. They catalogued stars, calculated orbits, and predicted eclipses decades in advance. But they also started noticing things that didn't quite fit. Take Uranus, for example. William Herschel discovered this planet in 1781, and astronomers immediately set about calculating its orbit using Newton's laws. But there was a problem. Uranus wasn't where it was supposed to be. Its orbit showed slight deviations from the predicted path. Now, these deviations were tiny. We're talking about tiny fractions of a degree. But Newton's theory was supposed to be perfect. Even tiny errors were troubling. Two astronomers, Abbé Leverrier in France and John Couch Adams in England, had a brilliant idea. What if there was another planet out there, pulling on Uranus with its gravity? They used Newton's laws to calculate where this hypothetical planet should be located. In 1846, German astronomer Johann Galle pointed his telescope at the predicted position and found Neptune, almost exactly where the calculations said it should be. This was Newton's theory, at its most triumphant, predicting the existence of an entire planet using nothing but mathematics and gravitational theory. But success breeds confidence, and confidence breeds carelessness. Fresh from their triumph with Neptune, astronomers tried the same trick with Mercury. Mercury's orbit showed an anomaly too. Its perihelion, the point closest to the Sun, was slowly rotating around the Sun. This precession had been observed since the 1840s, and it was tiny, about 43 arcseconds per century. That's less than the width of a human hair viewed from a mile away. Leverrier applied the same logic he'd used for Neptune. There must be another planet inside Mercury's orbit, tugging on it gravitationally. He even named this hypothetical planet Vulcan. Astronomers spent decades searching for Vulcan. They thought they'd spotted it several times, especially during solar eclipses, when a planet that close to the Sun might be visible. But Vulcan never materialized. No matter how hard they looked, no matter how sophisticated their instruments became, there was no planet inside Mercury's orbit. This was deeply troubling. Newton's theory had worked perfectly for Neptune, so why was it failing for Mercury? The discrepancy was tiny, but it was persistent and unexplainable. While astronomers were struggling with Mercury, physicists were dealing with their own set of problems, and these problems centered around light. Throughout the 19th century, scientists had figured out that light was an electromagnetic wave. This was a huge breakthrough, unifying electricity, magnetism, and optics into a single theory. But it created a new puzzle. Waves need something to wave in. Sound waves travel through air. Water waves travel through water. So what do light waves travel through? The answer seemed obvious. Light must travel through some kind of invisible medium that fills all of space. Scientists called this medium the luminiferous ether, and it was supposed to be everywhere, in empty space, between the atoms in solid objects, everywhere. But if the ether exists, Earth must be moving through it as we orbit the Sun. This should create an ether wind that affects the speed of light in different directions. In 1887, Albert Michelson and Edward Morley designed an incredibly precise experiment to detect this ether wind. They used an interferometer, basically a device that splits a light beam, sends the two halves in perpendicular directions, then recombines them to look for tiny differences in their travel times. The result? No ether wind. Zero. Nothing. No matter which direction they pointed their apparatus, no matter what time of year they conducted the experiment, the speed of light was always the same. This was impossible according to 19th century physics. If Earth is moving through the ether at 30 kilometers per second, our orbital speed, there should definitely be a detectable effect. But there wasn't. As if the ether problem wasn't bad enough, physicists ran into another wall with something called black body radiation. A black body is an object that absorbs all electromagnetic radiation that hits it. When you heat a black body, it glows. First red, then orange, then white, then blue-white as it gets hotter. Classical physics, based on Newton's mechanics and Maxwell's electromagnetism, made very specific predictions about how much energy a black body should radiate at each wavelength. These predictions worked fine for low frequencies, but at high frequencies, they went completely insane. According to classical theory, a black body should radiate infinite energy at ultraviolet frequencies. This became known as the ultraviolet catastrophe, and it was a disaster for classical physics. Real black bodies don't radiate infinite energy, obviously, since that would violate conservation of energy and probably destroy the universe. But classical physics couldn't explain why they didn't. Then there was the photoelectric effect. When light hits certain metals, it knocks electrons out of the surface. This seemed straightforward enough. Light carries energy, so it should be able to kick electrons around. But the details were all wrong. According to classical physics, brighter light should knock out electrons with more energy. Instead, the energy of the ejected electrons depended only on the frequency, color of the light, not its intensity, brightness. Even weirder, there was a threshold frequency below which no electrons were ejected, no matter how bright the light was. You could shine a dim blue light on a metal and get electrons, but no amount of bright red light would work. This made no sense classically. If light is a wave carrying energy, then brighter light should carry more energy and should always be able to knock out electrons if you make it bright enough. By 1900, classical physics was in crisis. The ether couldn't be detected. Black bodies radiated the wrong spectrum. The photoelectric effect behaved impossibly, and Mercury's orbit stubbornly refused to follow Newton's predictions exactly. Something fundamental was wrong with the classical worldview. The clockwork universe was breaking down, and physicists didn't know how to fix it. The solutions, when they came, would be so radical that they would completely overturn our understanding of reality. Space and time weren't absolute and unchanging. They were flexible and interconnected. Energy wasn't continuous, it came in discrete packets called quanta. Particles weren't just particles, they were also waves. And gravity wasn't a force at all. It was something far stranger, the curvature of space-time itself. As the 19th century ended, physics stood at a crossroads. The Newtonian worldview had been incredibly successful, but its limitations were becoming impossible to ignore. Two young physicists were about to change everything. Max Planck would solve the blackbody problem by proposing that energy comes in discrete quanta, launching the quantum revolution. And Albert Einstein would solve the Mercury problem by completely reconceptualizing the nature of space, time, and gravity itself. The clockwork universe was about to be replaced by something far stranger and more wonderful. But that's a story for our next hour. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published 4 papers that would completely revolutionize physics. His name was Albert Einstein, and he was about to make Newton's absolute space and time look as outdated as the idea that the Earth is flat. But here's the thing about Einstein that most people don't realize. He wasn't trying to overthrow Newton. He was trying to save physics from a growing pile of contradictions. Remember the Michelson-Morley experiment that couldn't find the ether? Einstein had a radical solution. What if there is no ether? What if light doesn't need a medium to travel through? What if the speed of light is always the same, regardless of how you're moving? This seems like a small change, but it's like pulling a thread that unravels the entire sweater of classical physics. If the speed of light is constant for all observers, and space and time can't be absolute and unchanging, they have to be flexible, dynamic, interconnected. Einstein called this special relativity, and it was just the beginning. Special relativity handled objects moving at constant speeds. But what about acceleration? What about gravity? Einstein had another brilliant insight, and it came from thinking about falling elevators. Imagine you're in an elevator and the cable snaps. As you fall freely, you don't feel the pull of gravity, you feel weightless, just like astronauts in orbit. Now imagine you're in an elevator in deep space, far from any gravitational source. If someone accelerates the elevator upward at 9.8 meters per second squared, you'd feel pressed against the floor with exactly the same force you feel standing on Earth. Einstein realized something profound. There's no way to tell the difference between gravitational acceleration and mechanical acceleration. This became known as the equivalence principle, and it led Einstein to a shocking conclusion. Gravity isn't a force pulling you down. Gravity is space-time itself being curved by mass and energy, and you're simply following the straightest possible path through that curved space-time. This is like discovering that what you thought was a force pushing you around a curve is actually the curve itself. To understand Einstein's idea, imagine space-time as a stretched rubber sheet. Now place a bowling ball, representing a massive object like the sun, in the middle of the sheet. The ball creates a depression, curving the sheet around it. If you roll a marble representing Earth across this curved sheet, it doesn't travel in a straight line. It follows the curve created by the bowling ball. From the marble's perspective, it's being pulled toward the bowling ball. But really, it's just following the straightest possible path through curved space. This is what Einstein proposed for gravity. Massive objects like stars and planets curve space-time around them. Other objects follow the curves, and we interpret this as gravitational attraction. But Einstein's theory made predictions that were dramatically different from Newton's. In Einstein's universe, time runs slower in stronger gravitational fields. Light bends when passing near massive objects. Nothing can travel faster than light. Mass and energy are interchangeable. E equals mc squared. Gravitational waves should ripple through space-time. These weren't just theoretical curiosities. They were testable predictions that would either validate or destroy Einstein's theory. Einstein's general theory of relativity, published in 1915, made a specific prediction about light. It should bend when passing near massive objects. Newton's theory also predicted light bending, but Einstein's prediction was exactly twice as large. The test would require observing stars near the sun during a total solar eclipse. Under normal circumstances, you can't see stars near the sun because it's too bright. But during an eclipse, when the moon blocks the sun's disk, you can photograph the stars around it. World War I delayed the test, but in 1919, British astronomer Arthur Eddington led expeditions to observe an eclipse from Principe, off the coast of West Africa, and Brazil. The results were dramatic. Starlight bent by exactly the amount Einstein predicted, twice what Newton's theory suggested. When the results were announced, Einstein became an overnight celebrity. The headline in the London Times read, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." But the real revolution wasn't just in physics, it was in how we understood reality itself. Remember Mercury's stubborn orbital precession that had puzzled astronomers for decades? Einstein's general relativity explained it perfectly, without needing to invoke any mysterious planet Vulcan. In Einstein's curved space-time, Mercury's orbit isn't a perfect ellipse that stays fixed in space. Instead, the ellipse itself slowly rotates around the Sun, creating the observed precession. The calculation was exact. Einstein's theory predicted Mercury's perihelion would advance by 43 arcseconds per century, matching observations perfectly. This wasn't just another successful prediction, it was the solution to a problem that had plagued astronomy for over half a century. Newton's theory, for all its successes, have failed to explain Mercury's orbit. Einstein's theory got it exactly right. For the first time since Newton, someone had improved on the fundamental theory of gravity. Einstein's equations didn't just describe gravity, they described the entire universe. And when Einstein first solved his equations for the universe as a whole, he got a disturbing result. The universe should be either expanding or contracting. It couldn't be static. This bothered Einstein so much that he added a cosmological constant to his equations to force the universe to be static. He later called this the greatest mistake of my life. Because in the 1920s, Edwin Hubble made an extraordinary discovery. Distant galaxies are moving away from us, and the farther away they are, the faster they're receding. The universe is expanding, exactly as Einstein's original equations had predicted. This led to an even more startling realization. If the universe is expanding now, it must have been smaller in the past. Extrapolating backward, there must have been a moment when everything in the universe was compressed into an infinitely small, infinitely dense point. This moment became known as the Big Bang, and it meant the universe had a beginning, something that seemed philosophically impossible to many scientists. Einstein's equations made another prediction that was so bizarre that even Einstein didn't believe it. Black holes. In 1916, Karl Schwarzschild solved Einstein's equations for the spacetime around a spherically symmetric mass. His solution showed that if you compress enough mass into a small enough space, the curvature of spacetime becomes so extreme that nothing, not even light, can escape. The boundary around this region is called the event horizon, and anything that crosses it is doomed to fall toward the central singularity, where the curvature becomes infinite and the laws of physics break down. Einstein thought this was a mathematical curiosity, not a physical reality. He wrote papers trying to prove that black holes couldn't actually form in nature. He was wrong. We now know that black holes are not only real, but common. There's a supermassive black hole at the center of our galaxy, and stellar mass black holes are scattered throughout the cosmos. But Einstein's revolution came with a price. His theory was purely classical. It describes space-time as a smooth, continuous fabric. Meanwhile, quantum mechanics was revealing that energy, matter, and even space and time might be fundamentally discrete and probabilistic. Einstein spent the last 30 years of his life trying to unify general relativity with quantum mechanics, seeking a theory of everything that could describe all the forces of nature in a single framework. He failed. The problem of unifying gravity with quantum mechanics remains unsolved to this day, and it's one of the greatest challenges in modern physics. But Einstein's legacy was secure. He had shown that Newton's absolute space and time were illusions. Reality was far stranger and more flexible than anyone had imagined. Space could stretch and compress. Time could speed up and slow down. Mass could bend the very fabric of reality. And gravity wasn't a force at all. It was geometry. The universe itself was curved, and we were all just following the curves. This was a revolution that changed not just physics, but philosophy, art, literature, and our entire understanding of what it means to exist in this strange, curved cosmos. But the story of gravity was far from over. As we'll see in our next hour, the 20th century would bring even more surprises. By 1930, physics had split into two incredibly successful but completely incompatible theories. General relativity governed the large-scale universe, planets, stars, galaxies, black holes. Quantum mechanics governed the microscopic world, atoms, particles, radiation. Both theories worked brilliantly in their respective domains. General relativity predicted the expansion of the universe, the bending of light, the precession of Mercury's orbit. Quantum mechanics explained the periodic table, chemical bonding, the behavior of semiconductors that would eventually lead to computers. But when physicists tried to combine them, disaster struck. Here's the problem. Quantum mechanics says that energy and matter are fundamentally uncertain and probabilistic. You can never know exactly where a particle is or exactly how much energy it has. General relativity, on the other hand, says that matter and energy curve space-time in precise, deterministic ways. So what happens when you try to apply quantum uncertainty to gravity? The calculations blow up. You get infinite answers to finite questions. The mathematics literally breaks down. This wasn't just an academic problem. It was a crisis that threatened the entire foundation of physics. The crisis becomes most apparent at something called the Planck scale. Distances of about 10⁻35 meters and times of about 10⁻43 seconds. These numbers are so small they're almost meaningless, but they represent the boundary where quantum effects and gravitational effects become equally important. At the Planck scale, quantum uncertainty becomes so extreme that space-time itself starts to fluctuate. The smooth, curved space-time of general relativity gets replaced by a foaming, bubbling quantum chaos where the very concepts of distance and time lose their meaning. Imagine trying to measure the surface of the ocean from an airplane. It looks smooth. Get closer in a boat and you see waves. Get even closer and you see ripples and foam. At the Planck scale, space-time is like that foam, constantly appearing and disappearing, creating and destroying tiny virtual black holes, completely unpredictable and utterly unlike the serene geometric landscape Einstein envisioned. This is where our understanding of gravity completely breaks down. We have no idea what happens to Einstein's beautiful theory when quantum effects dominate. Meanwhile, particle physicists were discovering that nature has four fundamental forces: electromagnetic, weak nuclear, strong nuclear, and gravitational. By the 1970s, they had successfully unified three of these forces into what's called the Standard Model of particle physics. The electromagnetic force and weak nuclear force were unified into the electroweak force. The strong nuclear force was described by quantum chromodynamics. Together, these theories could explain almost everything about particles and their interactions. Almost everything, except gravity. Gravity stubbornly refused to fit into the Standard Model. It was far too weak compared to the other forces, about 10 to the power of 36 times weaker than electromagnetism. And unlike the other forces, gravity couldn't be quantized, turned into a quantum field theory with particle exchanges. This created a bizarre situation. Physicists had a beautiful, mathematically elegant theory that worked perfectly for large-scale phenomena, and another beautiful, mathematically elegant theory, quantum mechanics, that worked perfectly for small-scale phenomena, but the two theories were fundamentally incompatible. It was like having two perfect maps of the same territory that showed completely different landscapes. In the 1980s, a new approach emerged that promised to solve the quantum gravity problem: string theory. Instead of treating particles as point-like objects, String theory proposed that everything in the universe, every particle, every force, consists of tiny, vibrating strings. Different vibration patterns correspond to different particles. The beautiful thing about string theory is that it naturally includes gravity. One of the vibration patterns automatically corresponds to the graviton, the hypothetical particle that carries the gravitational force. String theory also required extra dimensions, not just the 3 spatial dimensions and 1 time dimension we experience, but potentially up to 11 dimensions total. These extra dimensions are supposedly compactified, curled up so small that we don't notice them in everyday life. For a while, string theory seemed like the answer to everything. It promised to unify all forces, explain all particles, and provide a complete theory of everything. There was just one problem. String theory made virtually no testable predictions. As string theorists developed their mathematics further, they discovered something disturbing. There wasn't just one string theory. There were potentially 10 to the power of different versions. This number is so large, it's almost incomprehensible. There are only about 10 to the power of atoms in the observable universe. The number of possible string theory universes is larger than the number of atoms by a factor that has more zeros than there are atoms. Each of these universes would have different physical laws, different particle masses, different force strengths. Most of them would be completely inhospitable to life, or to anything interesting at all. This became known as the landscape problem. If string theory is correct, and our universe is just one tiny island in an vast ocean of possible universes, most of which are boring or hostile to complexity. Why do we happen to live in a universe with the right laws of physics to allow stars, planets, and life to exist? String theorists suggested that maybe all these universes actually exist in a multiverse, and we just happen to find ourselves in one of the rare universes that can support observers. This was deeply unsatisfying to many physicists. Science is supposed to make predictions, not explain away our observations by invoking an infinite number of unobservable universes. Not everyone was satisfied with string theory's approach. An alternative theory called loop quantum gravity took a different path. Instead of trying to quantize matter and energy in a smooth spacetime, it tried to quantize spacetime itself. In loop quantum gravity, space isn't continuous. It's made up of discrete, indivisible units at the Planck scale. Space is pixelated, like a digital photograph when you zoom in far enough. This approach avoided some of the problems of string theory. It didn't require extra dimensions or invoke multiverses, but it also couldn't easily incorporate the other forces of nature. Loop quantum gravity made some specific predictions. The Big Bang wasn't actually the beginning of time, but rather a big bounce where a previous contracting universe rebounded into our current expanding phase. Black holes don't have infinitely dense singularities at their centers, but rather extremely dense but finite cores. These predictions were testable in principle, but the energies and timescales involved were so extreme that actually testing them remained far beyond our current technology. While theorists struggled with quantum gravity, observational astronomers were discovering their own mysteries. In the 1970s, Vera Rubin and Kent Ford measured the rotation speeds of spiral galaxies and found something impossible. According to Newton's laws, and Einstein's for that matter, stars on the outer edges of galaxies should orbit much more slowly than stars near the center, just like planets in our solar system. But that's not what they observed. Stars throughout spiral galaxies were all moving at roughly the same speed. The outer stars were moving way too fast, so fast that they should have been flung out of the galaxy entirely. The only way to explain these observations was to assume that galaxies contain about 5 times more mass than we can see. This invisible mass became known as dark matter. Dark matter doesn't emit light, doesn't absorb light, and doesn't interact with ordinary matter except through gravity. It's completely invisible except for its gravitational effects. This was deeply troubling. Astronomers were essentially saying, we can explain how galaxies work, but only if 85% of the matter in the universe is made of something we've never detected and don't understand. Just when physicists thought dark matter was bad enough, the universe delivered an even bigger surprise. In 1998, two teams of astronomers studying distant supernovae made an shocking discovery. The expansion of the universe is accelerating. Not only is the universe getting bigger, it's getting bigger faster and faster. This was completely unexpected. Gravity should be slowing down the expansion, not speeding it up. The only way to explain accelerating expansion was to invoke something called dark energy, a mysterious form of energy that fills all of space and pushes the universe apart. Dark energy makes up about 68% of the universe. Combined with dark matter, 27%. This means that everything we can see and understand, all the stars, planets, galaxies, and gas clouds, represents only about 5% of the universe. We live in a universe that is 95% invisible and incomprehensible. This was the state of gravity research as we entered the 21st century. Two incompatible theories describing different scales, a landscape of untestable string theories, and a universe dominated by mysterious dark components that we couldn't detect or understand. The story of gravity had become the story of everything we don't know about the universe. But as we'll see in our next hour, new technologies and observations were about to provide some answers and raise even more profound questions. In 1916, just 1 year after publishing General Relativity, Einstein made another prediction that seemed almost too bizarre to be real. Gravitational waves. If space-time can be curved by mass and energy, Einstein reasoned, then accelerating masses should create ripples in space-time that propagate outward at the speed of light. These ripples would alternately stretch and compress space itself as they passed through. But Einstein immediately realized these waves would be incredibly weak. He calculated that even the most violent cosmic events would create distortions smaller than 1/10,000th the width of a proton. The waves would be so faint that Einstein himself doubted they could ever be detected. For most of the 20th century, gravitational waves remained a theoretical curiosity. Some physicists weren't even sure they were real. Maybe they were just mathematical artifacts with no physical meaning. But a few visionaries believed that if gravitational waves could be detected, they would open up an entirely new way of studying the universe. Instead of using light to observe cosmic events, we could use the fabric of space-time itself. The first indirect evidence for gravitational waves came from an unexpected source, a pulsar discovered in 1974 by Russell Hulse and Joseph Taylor. Pulsars are rapidly spinning neutron stars that emit beams of radio waves like cosmic lighthouses. This particular pulsar, designated PSR B193+16, was special because it was in a binary system with another neutron star. The two neutron stars orbit each other every 7.75 hours in an incredibly tight dance. Each star has the mass of our Sun, compressed into a sphere only 20 kilometers across. They're separated by a distance less than the diameter of our Sun. According to Einstein's theory, this system should be radiating energy away in the form of gravitational waves, causing the orbit to slowly decay. Hulse and Taylor measured the orbital period with incredible precision over many years and found that it was indeed decreasing by exactly the amount predicted by general relativity. The two neutron stars are spiraling toward each other at a rate of about 3.5 meters per century, losing energy to gravitational waves that ripple out across the cosmos. This was the first solid evidence that gravitational waves actually exist, and Hulse and Taylor won the Nobel Prize for their discovery in 1993. Inspired by the indirect evidence from pulsars, a small group of physicists began working on an almost impossibly ambitious project, directly detecting gravitational waves. The idea was conceptually simple, but practically nightmarish. You build two identical detectors in an L shape, each arm several kilometers long. You bounce laser light back and forth between mirrors at the ends of each arm. When a gravitational wave passes through, It should stretch one arm and compress the other by a tiny amount, changing the time it takes light to travel down each arm. But remember how small these distortions are. Less than 1/10 of Earth to the nearest star, to an accuracy smaller than the width of a human hair. The technical challenges were staggering. The mirrors had to be isolated from every possible vibration, earthquakes, ocean waves, traffic, even the thermal motion of atoms in the mirror supports. The laser light had to be stabilized to incredible precision. The entire system had to be kept in a perfect vacuum to prevent air molecules from interfering with the light. Many physicists thought it was impossible. The National Science Foundation was initially reluctant to fund such an expensive, high-risk project. But the LIGO, Laser Interferometer Gravitational Wave Observatory, team pressed on, building 2 identical detectors, one in Louisiana and one in Washington state, separated by 3,000 kilometers. LIGO began operating in 2002, but for more than a decade, it detected nothing. The instruments were incredibly sensitive, but not quite sensitive enough. In 2010, LIGO was shut down for a major upgrade called Advanced LIGO. The new detectors were 10 times more sensitive than the original design, able to detect distortions as small as 1/10,000th the width of a proton. Advanced LIGO came online in September 2015. On September 14, 2015, at 5:51 a.m. Eastern Time, both detectors simultaneously recorded a distinctive chirp signal that lasted only 0.2 seconds. The signal showed exactly the pattern predicted for 2 black holes spiraling toward each other and merging, starting at low frequency and low amplitude, then increasing in both frequency and amplitude as the black holes got closer and closer, finally ending in a burst of energy as they merged into a single black hole. The data revealed an astounding event. 2 black holes, one 36 times the mass of our Sun and the other 29 times the mass of our Sun, had merged 1.3 billion years ago. The merger converted 3 entire solar masses into pure gravitational wave energy in a fraction of a second, more power than all the stars in the observable universe combined. And we detected it as a whisper, a distortion of space and time so small that it took humanity's most sensitive instruments to deceive it. That first detection, designated GW15914, was just the beginning. LIGO and its European counterpart Virgo began detecting gravitational waves on a regular basis, black hole mergers of various masses. The first detection of merging neutron stars, GW117,817, intermediate mass black holes that had never been observed before, evidence for the population of black holes throughout the universe. Each detection was like receiving a message from the deep cosmos, telling us about events so violent and extreme that they could only be studied through their gravitational significance. The neutron star merger GW170,817 was particularly spectacular because it was observed simultaneously in gravitational waves and light. This multi-messenger astronomy confirmed that neutron star mergers are the source of many heavy elements in the universe, including gold and platinum. Gravitational wave astronomy was revealing a universe far more dynamic and violent than anyone had imagined. Black hole mergers were happening constantly throughout the cosmos. The universe was literally ringing like a bell, with gravitational waves from countless cosmic collisions. Gravitational waves don't just confirm Einstein's predictions, they're teaching us entirely new things about the universe. Black hole population. Before LIGO, we knew of only a few dozen black holes. Gravitational wave detections revealed that black holes are far more common than expected, with a wide range of masses. The history of star formation. The rate of black hole mergers tells us about when and how massive stars formed throughout cosmic history. Fundamental physics. Gravitational waves travel at exactly the speed of light, confirming another prediction of general relativity. They also provide new tests of Einstein's theory in the strong field regime, where gravity is incredibly intense. Cosmology, gravitational waves offer a new way to measure the expansion rate of the universe, potentially helping resolve disagreements between different measurement methods. The nature of space-time. Every gravitational wave detection is a direct observation of space-time curvature. We're literally watching the geometry of the universe flex and vibrate. The current generation of gravitational wave detectors is just the beginning. Future projects will be even more ambitious. Space-based detectors, the Laser Interferometer Space Antenna, will consist of 3 spacecraft flying in formation, creating a gravitational wave detector millions of kilometers across. LISA will be sensitive to much lower frequency waves, potentially detecting the merger of supermassive black holes and even primordial gravitational waves from the Big Bang itself. Third-generation ground-based detectors, projects like Einstein Telescope and Cosmic Explorer, will be 10 to 100 times more sensitive than current detectors, able to see black hole mergers across the entire observable universe. Multi-messenger astronomy, combining gravitational wave observations with traditional astronomy, will provide unprecedented insights into cosmic events. The detection of gravitational waves represents more than just a confirmation of Einstein's theory. It's the birth of an entirely new form of astronomy. For the first time in human history, we can observe the universe not just through electromagnetic radiation, but through the vibrations of space-time itself. We've learned to listen to the universe's deepest symphony, played on instruments of curved space-time by the most massive and energetic events in the cosmos. And we're only just beginning to understand what this cosmic music is telling us about the nature of reality itself. But even as gravitational wave astronomy opens new windows on the universe, the fundamental mysteries of gravity remain. We still don't know how to reconcile Einstein's theory with quantum mechanics. We still don't understand dark matter or dark energy. We still don't know what happens at the center of black holes or what caused the Big Bang. The story of gravity continues, and as we'll see in our final hour, some of the biggest questions are still ahead of us. We've come so far in our understanding of gravity, from Aristotle's falling objects, to Einstein's curved space-time, to LIGO's gravitational waves. But here's the thing that should keep you awake at night. We still have absolutely no idea why gravity is so ridiculously weak. Think about it. You can pick up a paperclip with a small magnet, easily overcoming the gravitational pull of the entire Earth. The electromagnetic force holding atoms together is 10 to 36 times stronger than gravity. That's not just a big number, that's incomprehensibly huge. If gravity were just slightly stronger, stars would burn out in thousands of years instead of billions. If it were much weaker, stars wouldn't form at all. The fact that gravity has exactly the right strength to allow a universe with long-lived stars, stable planets, and complex chemistry seems either incredibly lucky or deeply meaningful. This is called the hierarchy problem, and it's one of the deepest mysteries in physics. Why is gravity so weak compared to the other forces? Is there something special about our universe, or are we missing something fundamental about the nature of gravity itself? One possible solution to the hierarchy problem involves extra dimensions, and not just the tiny curled-up dimensions of string theory, but large extra dimensions that we somehow can't perceive directly. Here's the idea. What if gravity appears weak because it's actually spreading out into dimensions we can't see? Imagine you're a two-dimensional being living on the surface of a sheet of paper. If someone shines a light from above the paper, most of the light goes off in directions you can't perceive. Only a tiny fraction illuminates your 2D world. Maybe gravity works the same way. The true strength of gravity might be comparable to the other forces, but most of its influence spreads out into extra dimensions, leaving only a tiny residue in our familiar three-dimension space. This isn't just wild speculation, it makes testable predictions. If large extra dimensions exist, gravity should become stronger at very short distances as you approach the scale of these extra dimensions. Experiments have been conducted to look for deviations from Newton's inverse square law at microscopic scales, So far, gravity behaves exactly as Einstein predicted, down to distances of about 50 micrometers, roughly the width of a human hair. But if extra dimensions exist, we might see deviations at even smaller scales. Another approach to the mysteries of dark matter and dark energy is to ask, what if the problem isn't with our understanding of matter and energy, but with our understanding of gravity itself? Modified Newtonian dynamics, MOND, proposed by Mordechai Milgram in 1983, suggests that Newton's laws break down at very low accelerations, like those experienced by stars in the outer regions of galaxies. Instead of invoking dark matter to explain galaxy rotation curves, Mond proposes that gravity behaves differently when accelerations are extremely small. The theory has had some remarkable successes, predicting the observed properties of many galaxies without requiring any dark matter. Other modified gravity theories, like F(r) gravity and scalar tensor theories, modify Einstein's equations to produce cosmic acceleration without dark energy. These theories face significant challenges. They often have trouble explaining the full range of astronomical observations, and they sometimes make predictions that contradict laboratory experiments. But they represent a legitimate alternative approach to the dark matter-dark energy paradigm. The question is, are we dealing with new forms of matter and energy that we don't understand? Or are we dealing with modifications to gravity that we haven't discovered yet? The ultimate goal of theoretical physics remains the unification of general relativity and quantum mechanics into a theory of quantum gravity. This isn't just an academic exercise. Understanding quantum gravity is essential for answering some of the deepest questions about our universe. What happens at the center of black holes? What caused the Big Bang? Is time travel possible? Are there other universes? What is the fundamental nature of space and time? String theory remains the most developed approach to quantum gravity, but it continues to face the problem of making testable predictions. Loop quantum gravity offers an alternative, but it struggles to incorporate the other forces of nature. Other approaches include emergent gravity. Maybe gravity isn't fundamental at all, but emerges from more basic quantum phenomena, like temperature emerges from the motion of atoms. Causal set theory. Maybe space-time is made of discrete, indivisible units connected by causal relationships, a kind of quantum foam at the deepest level. Asymptotic safety. Maybe gravity becomes simple and predictable at extremely high energies, making it possible to calculate quantum gravitational effects. Each approach offers insights, but none has yet provided the breakthrough that would unlock the mysteries of quantum gravity. End quote. Flow, S.S., says it can best be done as the process of quantum gravity. Black holes represent the ultimate testing ground for our theories of gravity. They're places where space-time curvature becomes so extreme that our normal intuitions completely break down. Recent observations have revolutionized our understanding of black holes. The Event Horizon Telescope captured the first direct images of black hole event horizons, confirming many predictions of general relativity, while raising new questions about how matter behaves in extreme gravitational fields. Gravitational wave observations have revealed that black hole mergers are common throughout the universe, and that black holes can spin at nearly their theoretical maximum rates. But black holes also present us with profound puzzles. The information paradox. According to quantum mechanics, information can never be destroyed. But anything that falls into a black hole seems to disappear forever when the black hole eventually evaporates through Hawking radiation. This contradiction between general relativity and quantum mechanics remains unresolved. The firewall paradox. Recent theoretical work suggests that the event horizon of a black hole might be a firewall that incinerates anything that tries to cross it. This contradicts the equivalence principle, which says that falling into a black hole should feel like free fall. Naked singularities. Do singularities always hide behind event horizons, or can they exist naked, visible to the outside universe? This question goes to the heart of what happens when general relativity breaks down. One of the most controversial ideas in modern cosmology is the multiverse, the possibility that our universe is just one of countless universes with different physical laws and constants. This idea arises naturally from several areas of physics. Eternal inflation, the theory that our Big Bang was just one bubble in an eternally inflating multiverse, with different regions having different physical properties. String theory landscape, the possibility that there are 10 to the power of different ways to set up the laws of physics, each corresponding to a different universe. Many worlds quantum mechanics, the interpretation that every quantum measurement creates parallel universes corresponding to different possible outcomes. If the multiverse is real, it might explain why our universe has exactly the right properties to support complexity and life. We don't live in a specially designed universe, we just happen to live in one of the rare universes where observers can exist. But many physicists are deeply uncomfortable with multiverse theories because they seem to put entire realms of reality beyond the reach of scientific investigation. How can we test theories about unobservable universes? This tension between theoretical elegance and empirical testability represents one of the biggest challenges facing modern physics. As we look toward the future, several exciting developments promise to advance our understanding of gravity. Quantum experiments in space, experiments on the International Space Station and future space missions will test quantum mechanics and general relativity in regimes that are impossible to access on Earth. Precision tests of general relativity, new generations of atomic clocks, gravitational wave detectors, and astronomical observations will test Einstein's theory with unprecedented precision. Artificial intelligence and big data, machine learning algorithms are already helping to analyze gravitational wave data and discover new astronomical phenomena. AI might help us find patterns in data that reveal new physics. Fundamental physics experiments, particle accelerators, dark matter detectors, and other experiments might finally provide clues about the quantum nature of gravity. Space-based gravitational wave detectors, LISA, and future space missions will open up entirely new frequency ranges for gravitational wave astronomy. The next few decades promise to be as revolutionary for our understanding of gravity as the early 20th century was for our understanding of space and time. As we reach the end of our journey through the history of gravity, it's worth reflecting on how far we've come and how far we still have to go. We started with ancient humans wondering why things fall down. We've ended up with gravitational wave detectors that can measure distortions in space-time smaller than 1/10th the width of a proton. We started with Aristotle's confident but wrong pronouncements about heavy objects falling faster than light ones. We've ended up with Einstein's mind-bending revelation that gravity isn't a force at all, but the curvature of space-time itself. We started with Newton's clockwork universe, where everything was predictable if you just had enough information. We've ended up with a quantum mechanical cosmos, where uncertainty is fundamental, and where 95% of the universe consists of mysterious dark matter and dark energy that we can't see or understand. The story of gravity is the story of human curiosity and ingenuity. It's the story of people who refuse to accept that's just how things work as an answer. It's the story of mathematical insights so profound that they changed our understanding of reality itself. But it's also a story that's far from over. The deepest questions about gravity, how it relates to quantum mechanics, what dark matter and dark energy are, whether extra dimensions exist, what happens inside black holes, remain unanswered. Future generations will look back on our current understanding of gravity the way we look back on Aristotle's physics, as a noble but incomplete attempt to understand the workings of the cosmos. The universe is under no obligation to make sense to us, but somehow, against all odds, it does. The same mathematical relationships that govern falling apples also govern the motion of galaxies. The same geometric principles that describe curved surfaces also describe the fabric of space-time. We live in a universe where the laws of physics are not only comprehensible to human minds, but beautiful, elegant, and profound. That might be the greatest mystery of all. Gravity brought us down from the trees, but understanding gravity has lifted us to the stars. And this story, This incredible, ongoing story of human beings trying to understand the force that shapes the cosmos. This story has only just begun. Thank you for joining me on this journey through the history of gravity. From Aristotle to Einstein, from falling apples to gravitational waves, we've explored how humanity's understanding of this fundamental force has evolved over more than 2 millennia. The next time you drop something and watch it fall, remember, you're witnessing the same phenomenon that keeps planets in orbit, creates black holes, and shapes the large-scale structure of the universe itself. You're seeing space-time curvature in action. And who knows, maybe you'll be inspired to help write the next chapter in this incredible story.